Let's start with how an electric vehicle actually works. Now this is a test rig and it's a great way to see all the key components that actually go into an electric vehicle and give me an extremely easy way to explain how each bit works and interacts with each other. Now this is an electric vehicle battery pack and they come in lots of different form factors. Normally they're flat in the bottom of a vehicle and it makes it into a structural member, and they contain lots and lots of key components to simplify the build process for electric vehicle manufacturers. Now there's some key bits within this battery pack. There is a battery management system, and that basically manages every single cell within the battery pack. Now normally these are at 400 to 800 volts depending on the make and model of vehicle, and basically the BMS will monitor each individual cell group within the battery and make sure they're all within normally 0.2 millivolts of each other. Now the closer they are in balance, the more capacity the battery will have, as basically when charging or discharging, it's only as good as its strongest or weakest cell, or highest and lowest voltage cell. So the BMS has a really important job of monitoring all those cells, making sure they're close in balance, and it also monitors all the temperatures within the battery pack to make sure they don't exceed the temperature or go too low in temperature, which then affects the charging and discharging rate of the battery. Now in here there's also some other key parts, basically the high voltage contactors. So there'll be a positive and a negative contactor, and those are basically open if the vehicle was powered down or not charging to stop any power coming out of the battery pack, or in case of emergency if the vehicle needs to be shut down, normally there'll be a pyro fuse and a safety system that basically opens the contactors if anything was to ever happen, if the airbags went off, or in case of a crash. Now within the battery pack you'll also have a fuse. Now this fuse will be rated for normally the continuous power draw, and it's normally there to protect things like the high voltage cabling. So it'll be sized based around that size, so if something happened, a cable cut through, anything happened, the fuse would then blow, and in theory the battery would go open circuit, so no power is coming out of it. You normally have also a pre-charge resistor in there, and what a pre-charge resistor do is when you first power the battery up, it will basically slowly bring the voltage up. When I say slow, it's normally within a second, so pretty quick, but basically slowly brings that voltage up from 0 to 400 or 800 volts, depending on the system, so that all the other components in the system's capacitors can charge up, meaning you don't blow any parts. Without a pre-charge, there would be fundamental damage done quite quickly to the other high voltage components. Now, I'm going to show you what's inside of one of these batteries and how they're actually built. Now, this is a battery module. And inside the battery module, you have battery cells. Now, there'll be a number of these modules in an entire pack, and then there's a number of cells within each module that are linked in parallel, groups of 3 as you can see here, and then they're linked in series. So parallel increases the current available, and in series, as it compounds, it increases the voltage. Now, the cell type in these modules is a prismatic battery cell, as you can see here, and normally there's multiple pouch cells within here with the nice connectors on them, and they are a hard case, making them an easy form factor to produce modules from, which can then be linked together in series to produce complete battery packs. Now, in order for an EV to actually move, it doesn't just need the battery, it actually needs a propulsion system, meaning a motor. Now this is an AC motor, which is the most common form factor you'll find in most electric vehicles, and they come in a range of different form factors with gearboxes and inverters potentially built into them. Now I'm going to show you what the rotor looks like that sits within this motor. This is the rotor that sits within the motor. As you can see, it has bearings on either side. Now this is actually magnetic. As you can see here, you can actually see the magnetic fields that sit within the rotor. Now, there's one key part I haven't showed you, which is the inverter, and that takes the DC from the battery, converts it to AC to actually propel the vehicle along. This is an electric vehicle inverter. Now, this is an aftermarket inverter. A lot of EVs have these actually built into the motors now, but it's a great example for me to take the lid off and show you what's inside. Now in here you have the DC from the battery comes in on these two, and then the AC comes out here to go to the AC motor, and you've got some current sensors, and then hidden down inside here you have power electronics and IGBTs, which do all the switching to allow the motor to be controlled and move the vehicle forward. Now the battery stores energy, but you need to get energy into the battery in the first place, so you need something called a charge port. Now this is a type 2 charge port. There's also type 1, depending on what part of the world you're in. There's also something called a DC rapid charger. So this takes AC, but you may see some which have additional 2 pins at the bottom, which actually take DC directly in from a special rapid charger, which can be up to 300 kilowatts or even faster. And you'll see that on most OEM vehicles. Now, if you are doing AC charging from the grid, you need an onboard charger. Now, this is an OBC. It takes power in from the grid, converts the DC to go into the high voltage battery pack in order for it to charge up. But you also need something else, because electric vehicles don't just run on 400 or 800 volts. They also need a 12 volt system. So this is a DC to DC. It basically takes high voltage from the battery pack, converts it down to 12 volts to power up all the ancillary systems in the vehicle, meaning your stereo, your headlights, even the battery management system and the contactors need a 12 volt system to operate. There is a Q&A at the end of this video, so please do think of any questions you want to ask me and I'll be happy to answer them. It's now time to talk about retrofit. And I mean retrofit as in can take an old classic car and convert it to electric, or an old commercial vehicle, rather than scrapping it. Now this is a classic Mini, as you can see, but within here, there's actually a complete electric vehicle system fitted. Now this takes about 2 days to fit, as this kit has been specifically designed to fit the Mini for BMW for their classic Minis. Now I'm going to show you exactly what the kit looks like before it's fitted into this car. As you can see, that is the Mini. This is the kit that goes inside of it. This is broken down into key parts. Obviously you have a complete subframe here, which is the original Mini subframe. This actually bolts up into the Mini and picks up on the original mounting points. So there's no modification done to the chassis of the car. Everything is bolt-in. We then have a battery pack in the front here, which has 5 modules in. We have our inverter. We have our motor under here and a single speed reduction gearbox that goes to axles that come out. And then we have a small liquid cooling system to look after the motor and the inverter to make sure they stay at optimum temperature. Moving around, we then have a rear battery pack, which has the remainder of the battery modules. Each battery pack does also have a safety disconnect in, but by splitting the pack up, it allows us to keep the weight distribution correct on the Mini, so it still handles the same, and it's actually within 5 kilos of its original weight. And then we have the charge port, which is a Type 2, but it can also be a Type 1 for charging up the Mini, depending on whether it's in the UK, Europe, US, or any other place around the world. Now, this can be done for other commercial vehicles, trucks, vans, small classic cars, or day-to-day commuters. As the price of EV parts do come down, you may see retrofit becoming more and more of a commonplace, and it saves vehicles being imported into the country if you can retrofit them to electric. I mean, this will do 110 miles WLTP, which is probably perfect for small island communities and smaller locations which don't need to do large mileage. Now, in the boot of the Mini is where you keep obviously your charging cables and that sort of stuff, but you also have a battery pack hidden under here. So this is the battery pack you saw a minute ago, and it tucks in under here where the spare wheel used to go on the car and picks up on the original subframe mounting points. Then you have your charger, and then here you have a little button that you press to unlock the charging point. Now inside the car it still looks like a classic because it has original style gauges, but these now show different data. So we have kilowatts, which is the amount of power being used, and that is kilowatts you're using, but also kilowatts you're putting back into the car, because that's regenerative braking, where it can basically salvage energy when you're going down a hill or braking to put back into the battery pack. Then you have miles per hour, which can also be kilometers per hour, and you have temperatures. So you have your battery temperature, your motor temperature, and you have your state of charge, 0 to 100%, to tell you how much battery you've actually used. Now you have a throttle pedal replacement, which replaces the original. Brake pedal stays the same. Remove the clutch if it did have one, because it's now single speed. And you have a gear shifter. So this is a gear shifter to drive neutral reverse, but it's still a shifter. Just because, well, why would you not want it to still feel like a classic Mini and keep the shifting the same? One big question we always get is what happens to electric vehicles and their batteries when they get accident damage like this, or they get near end of life? Now there is a very good solution. Now, before I talk about the recycling of EVs and some of the amazing things we can do with the high voltage battery packs for energy storage, let's explain about the environmental impact, because I do get asked an awful lot, is, are EVs actually better for the environment when you take into account the production of the high voltage battery pack? And the short answer is yes, but here's why. After a vehicle has covered 20 to 30,000 miles, an EV is environmentally better. And throughout its lifetime, it will actually output 70% less CO2, and if it's then charged by renewable energy, that figure is even lower. The other key takeaway is air quality and noise pollution. EVs are silent, which is great for island life because you don't hear petrol diesel vehicles driving around, and you're also not breathing in particulates and CO2 that is expelled from those petrol and diesel engines, which has a massive impact on the environment, the ecosystem and marine life, and you lose the risk of oil spills and petrol and diesel spills, which can have drastic effects on everything around it. Now let's talk about recycling of electric vehicles. What happens when an EV reaches end of life? I mean, whether it's accident damage like this Tesla next to me, or whether it's just high mileage or extremely old, there's still a huge amount of value in the vehicle and the parts. And if they're recycled correctly, it really helps us move in towards more of a circular economy. Now, the parts that are good on this car can be taken off, and they can be used to repair and keep other vehicles on the road. But also the battery pack can come out of it and be used for energy storage. So whether it's an accident damaged car, or maybe it's a really high mileage car where the battery may have degraded between 70 and 80%, so it's not seen fit for road use, that battery can come out and be used in a second life application for another 15 to 20 years in energy storage. This is where we connect the dots. This is QUBE, an energy storage and charging infrastructure device that uses those second life EV batteries that I've just spoken about. Now the key thing is it charges up with solar, wind, hydro, and then it can be utilized when needed, meaning power houses, businesses, or recharge those electric vehicles even if the grid is down. Now I'm going to talk to you in detail about this QUBE and exactly how it works and how it's built. Let's talk about the outside of the QUBE first. So it's a 10-foot ISOC container, which is actually cut down from a 20-foot, so recycled. It has a 7 kilowatt AC charger built in on either side, and it can also have CCS rapid charging built in, that we can use the battery power to output huge amounts of electricity to do rapid DC charging. We then have power in and out. So in the side of it, we have AC power going in, or we can have solar, wind, hydro going directly in via DC. And then we have AC outputs, which can go to things like houses, businesses, and pavilion charging stations, which I'll show you about in a little bit. Now let's explain the inside of it and exactly how this thing works. Let's show you the inside of QUBE. Now within this setup, this has 2 Tesla battery packs, giving it 150 kilowatt hours, but they can actually stack up to 6 high, giving 450 kilowatt hours of battery power within this 10-foot container. We then have a large solar inverter. This is a 50 kilowatt inverter, but you could run 2 to 3 of these within here with ease, or you can run a custom power electronics unit for doing DC rapid charging and other things. It then has solar and wind direct input, has a cloud-based system for monitoring and looking after itself. And then we have the DC lines that come in here. So this inverter can do up to 1,000 volts in. So you can basically run the batteries in series and parallel and then feed them directly into the inverter. We then have power coming in from external, whether it's a generator. This system can actually turn on and off the generator. So what you could actually do is have a super efficient generator running at peak efficiency. This system, when it hits say 20% battery, can turn the generator on, run the generator for a period of time in its efficiency band, then shut the generator down, run the battery for the remainder of the time. So if you do have biofuels, this could be a really good advocate to run alongside it. So that's your power in there. You have a shutdown for the 12-volt system in case of emergency. You can shut the system down. And then you have output fuse box, which does the AC outputs to go to the supplies to houses, businesses, car charging points and things like that. There's then also a liquid cooling system up here, which basically manages the temperature within the battery packs and the container to keep them at peak efficiency and to make them happy for long periods of time. Now this should be able to operate for 15 to 20 years on second life batteries based on the research we have done. And we then also have a link here which is 4G, which then means we can monitor these anywhere in the world at any point in time to make sure they are online and reliable as possible. Alongside the energy storage, you need charging infrastructure. And that's because with charging infrastructure, EV adoption is quicker and easier. You'll hear things like range anxiety, which I don't think you're going to see in Caribbean islands because they're fairly small and most electric vehicles will do over 300 miles minimum per charge these days. But if you've got good charge infrastructure deployed in the correct locations, it will allow EV adoption to happen faster. And if the energy is produced throughout the day via solar, stored, and then can be deployed at night via charging infrastructure, it will make ownership of an EV considerably cheaper, taking into account the fact that cars are slightly more expensive to buy at the start compared to a petrol diesel counterpart right now. Now these are easy to deploy. In UK, Europe, they don't need planning permission. I'm not exactly sure what the rules are in the Caribbean, but you're not digging anything up. You sit them in place, you run some cradle tray in, so you're not doing any environmental damage or digging things up. And it allows you to learn where you need the chargers around the islands. And then long term, you can potentially decide to put permanent infrastructure into those locations once you've proven their use in that location. Transitioning to clean energy has never been easier. With the mass production of solar panels, battery energy storage, and EVs, it's never been a better time to make the transition. Why not power paradise with clean energy?